friends, welcome to video lecture on dynamics of machinery. In the today's video lecture, we'll discuss about free damped single degree of freedom vibration system session 2. So let's start our discussion. The contents for our discussion are viscous damped system. So under this we'll cover the three different systems such as over dam, critical dam system, then under dam system. For that, consider a classical spring mass damper as shown in figure. So here, when we consider the spring mass and damper system, so when we pull this system in downward direction, the system will displace by this one x distance. So at the same time, if you look towards this one, this is nothing but the displace diagram of the spring mass and damper system. So during this displaced position, the various forces are acts on this system, such as accelerating force. The next one, these are nothing but the external forces. So accelerating force comes in the direction of motion of this mass, okay, and the two forces will act in opposite direction of the motion of this mass or block. So by using the Newton's second law of motion, this equation can be written in this way: mx double dot, okay, this is nothing but this force x double dot along with the mass is nothing but the accelerating force that will act in downward direction. So as per sign convention, you have to consider the positive sign for the downward force. So mx double dot must be positive, and kx, this is nothing but the spring force, and this is nothing but the damping force. Both the forces acts in upward direction, so we have to give the minus sign for the same. So as per Newton's second law of motion, we know accelerating force equals to summation of external forces. So in this way we can develop the differential equation, okay. So mx double dot equals to minus cx single dot minus k into x. If I take both the term towards the left side, then the equation will changes like this one: mx double dot plus cx single dot plus kx equals to 0. Equation number 1 for this. This is a linear differential equation of the second order, and its solution can be written as x equals to e raised to st. Now differentiate this equation with respect to time t. So dx by dt equals to the differentiation of this x with respect to time t is nothing but here dx by dt. You can just replace this dx by dt by x single dot, okay. This indicate the velocity. So what's about this one, derivative of this term with respect to time t? So e raised to st, this term will remain as it is. Again derivative of this st is nothing but s. So simply you can get dx by dt equals to x single dot equals to s into e raised to st. Now again take the derivative of this term, okay. So d2x by dt square equals to, instead of this x single dot, x double dot will come. Now again the derivative of this term, the s will remain constant as it is. Again the derivative of this one with respect to time t is nothing but e raised to st, and again derivative of this st is nothing but s. So s multiplied by s square will come. So s square into e raised to st. Now substituting the value for this x single dot and x double dot in equation number 1. So the equation 1 will changes by substituting the values of x single dot and x double dot, okay, like this one. So you have to replace this x double dot by s square into e raised to st, and next one x single dot here by this term s into e raised to st, okay, plus next one x you have to replace by e raised to st, like this one. Now from this all the terms, just take this e raised to st as common, and now whatever the part remains, just put that part in one bracket. So e raised to st automatically becomes 0. So this equation with us m s square plus cx plus k equals to 0. Give equation 3 for this one. So equation 3, is called the characteristic equation of the system, which is a quadratic in terms of S. The two values of the S are given by, as this is the quadratic equation, we know how to get the roots of this quadratic equation. Okay, so S12 is nothing but minus B, as per actually we know the solution of differential equation ax square plus bx plus c equals to 0. From that relation we know minus b, so middle term here, minus b means here minus c plus or minus square root of b square minus 4ac, means here b square means here c square minus 4a term, coefficient of this one is m, okay, and k is nothing but here constant term, divided by twice a means here 2m will comes. So after adjustment, okay, readjusting the term, you can get S12 equals to minus c by 2m. Just separate this 2m here, okay, divide this 2m by this term as well as this term. Take this 2m instead of the square root sign, okay. So square root of the first term square, c divided by 2m whole bracket square minus k by m. Here in this case, if you take this inside of the square root sign, this is nothing but the 4m square, means here 1m get cancelled, okay, then 4 get cancelled. So in this way we can get the two solutions for S. Okay, give equation number next for this one. So the general solution for equation number 1 may be written as, so equation number 1 is here. So general solution for this one can be written in this way: x equals to c1 into e raised to s1t plus c2 into e raised to s2t. Just give equation number 5 for this, where this c1 and c2 are arbitrary constants which can be determined from the initial conditions. Now in equation number 4, the values of s1 equals to s2. Now if you just see this equation, when the value of this one s1 and s2 becomes equal, if you look towards this equation, when this value and this value becomes equal, in short c divided by 2m whole bracket square equals to k by m. When this term and this term becomes equal, automatically s12 becomes equal. So whatever the part written inside of that bracket, we'll just write it here: c divided by 2m whole bracket square equals to k by m. We know the meaning for this k by m, okay. Square root of if I take the square root from both the side, what do we get here? C divided by 2m equals to square root of k by m. We know the meaning for this one. This is nothing but the natural frequency of the given system, so we can indicate that by this sign omega n, okay. Give equation number next for this one. Now what's about this c? C equals to, if I take this 2m towards this side, right side, then we can get this relation c equals to 2m into omega n, which is the property of the system and is called critical damping coefficient and is represented by Cc. That is, critical damping coefficient Cc equals to 2m into omega n. The ratio of actual damping coefficient C and critical damping coefficient Cc is called damping factor or damping ratio and is represented by zeta. That is, zeta equals to C divided by Cc. Equation number next for this one, equation number 7. So in equation number 4, this one, equation number 4, C divided by 2m can be written as c divided by 2m. Just adjust one cc here, okay. So c divided by cc multiplied by cc divided by 2m. So what's about the meaning for this one? This is nothing but the zeta. And what's about the meaning for this one? This is nothing but here, if I take this 2m here, okay, you can get omega n. So zeta into omega n, we can get the value for c divided by 2m. Therefore S12, this relation S12 so S12 is nothing but here you have to replace this c divided by 2m term by zeta into omega n. So look towards this one, you have to replace this term c divided by 2m by zeta into omega n. So minus zeta into omega n will come here, plus minus again inside of the bracket zeta into omega n whole bracket square minus here omega n. In this way the equation will changes, omega n square will come, okay, towards the next part of this one. So if I take the omega n common from this square root sign and take outside of this square root sign, then whatever the part remains here is nothing but minus zeta plus or minus square root of, here only zeta will remain, so zeta square minus 1 into omega n. Give equation number next for this. Now the system can be analyzed for three different conditions. First one, zeta is greater than 1, that is c is greater than cc, which is called overdamped system. Second one, when zeta equals to 1, that is c equals to cc, which is called critically damped system. Third one, zeta is less than 1, that is c is less than cc, which is called underdamped system. So depending upon the value of zeta, the value of s in equation 8 will be real and unequal, real and equal, and complex conjugate respectively. So let us start with the first condition, analysis of overdamped system, that is zeta is greater than 1. In this case, the values of s are real and are given by this one, s1 equals to, now just focus on this one, this relation, s12 equals to minus zeta plus or minus square root of zeta square minus 1 into omega n. So as per here, when the value of zeta is greater than 1, okay, so as per this discussion, when the value for zeta is greater than 1, the equation will come like this one, this equation, the two values of s will comes in this way, s1 equals to minus zeta plus square root of zeta square minus 1 into omega n, and second one s2. So here the second value will come, first one plus and second one minus, so second value will come like this one, s2 equals to minus zeta square minus 1 into omega n. Then the solution of the differential equation becomes, now we know the general equation or general solution for this one, x equals to c1 e raised to s1t plus c2 into e raised to s2t. So from this relation we can write this one in this way, x equals to c1 into, so what's about this e raised to s1t, so whatever the s1 and s2 here with us, you have to replace this s1 and s2 by this term, this one and this one. So in place of this s1, write this term, so you can get this x equals to c1 into a raised to minus zeta plus square root of zeta square minus 1 into omega nt plus c2 into e raised to s2 means here this term s2t, s2 means here minus this term minus zeta minus square root of zeta square minus 1 into omega n into t. So this is the final solution for an overdamped system, and the constant c1 and c2 are obtained by applying initial conditions. Typical response curve of the overdamped system is as shown in this figure, okay. The amplitude decreases exponentially with the time and becomes 0 at t infinite. If you look towards this one, whatever the amplitude here and whatever the time relations with us, so system Actually here this line almost shown here parallel with this time axis, means this is not reaches up to this one time axis. Okay, so that will take infinite time. This is called aperiodic motion. Okay, now to get the value for this C1 and C2, let us imagine the body is to be displaced through a distance x naught from the equilibrium position and released without any initial velocity. Then these are the initial conditions with us: x equals to x naught at time t equals to 0, and the velocity, this one, with 0 velocity at time t. So displacement time plot of an overdamped system with general initial condition. For that, just differentiate the previous equation with respect to time t. Previous means here equation number 9. You have to differentiate this equation number 9 with respect to time t. Okay. So for that, if you look towards this one, this is the constant term. This is also constant term. Okay. So to differentiate that equation number 9 with respect to time t, okay, dx by dt equals to x single dot equals to c1 term. Okay, this is the constant term. This term will remain as it is. You have to differentiate this term. Okay, so e raised to this term will remain as it is. Again, derivative of this term is nothing but this term will come. Okay, extra this term will come here. Okay, means in this way c1 into bracket this one minus zeta plus square root of zeta square minus 1 omega n, this term will come. Okay, so here this term will come as it is here. So e raised to this term will remain as it is, plus a similar case with the next one, minus, sorry, this one plus c2 this term. Sorry, we are just focusing on equation number 9. This term c2 will remain as it is. You have to differentiate this term with respect to time t. So this term comes here and rest of this term will remain as it is. So here you can get c2 into minus zeta minus square root of zeta square minus 1 omega n. This term comes here. Okay, and e raised to this term will remain as it is. Substituting in the equations giving x and x single dot, the initial condition of equation number 10 we have. Now if we apply the initial condition for this one, so here we can get x naught. If I apply the initial condition, means here x equals to x naught at time t equals to 0 and x single dot equals to 0 at time t equals to 0. Okay, so this is the case of displacement, means if I here substitute the value for x equals to x naught and a next term, that is time t equals to 0, if I substitute the value for time t equals to 0, means e raised to 0, e raised to 0 is 1 here. Again the same case with this one, e raised to this term multiplied by omega n, this term becomes 0. Okay, means we can get x naught equals to c1 plus c2. In this way we can get the first equation, x naught equals to c1 plus c2. Now focus on the next one. So here the next condition with us, x single dot equals to 0 at time t equals to 0. Okay, so x single dot is 0, just substitute here 0, and at time t equals 0, so where we found the value of t, just substitute the, or just replace it by 0. So e raised to this term becomes 0. Similarly, e raised to this term becomes 0. E raised to 0 means 1. Okay, so what do we get here? c1 into this bracket will remains as it is. This one, this term will remains as it is. Similar case with this one, this term will remains as it is. Now solve this equation and this equation. For that, multiply by this equation if you want to get the value for c1. Okay, for that to remain the c1, you have to just eliminate c2. Okay, similar case with the c2. Okay, in this way you can get the value for, just solve these two equations by multiplying then subtracting. Okay, so you can get the value for c1 as into bracket zeta plus square root of zeta square minus 1 into x naught divided by 2 into square root of zeta square minus 1. Similarly, next one, C2 equals to in bracket minus zeta plus square root of zeta square minus 1 divided by 2 into zeta square minus 1 into x naught. Okay, this is the values for C1 and C2. Already the equation, this equation with us, we know the value for C1 and C2. Just substitute here and get the value for x. So x is nothing but C1 value with us. Okay, so you have to replace this C1 by this term. Okay, so C1, just substitute the value of C1 okay here. I forget to just replace this one. Okay, C1 x naught divided by 2 into square root of zeta square minus 1. Don't consider this C1. Okay, so minus zeta plus square root of zeta square minus 1. This term will remain as it is, plus you have to replace this C2 term by this one, this term. Okay, this term is taken common. Okay, so this is nothing but the C2 and this term will remain as it is. Okay, this term will remain as it is. You can get equation number, next one, equation number 11. So next one, so in this way get the relation for x by considering the underdamped, overdamped system. Okay, so since the power of E is negative in both the terms in the above equation, if you look to us here, the power of E is negative. In the above equation, they both decrease exponentially with t, and so x decreases as time t increases, becoming 0 at t equals to infinity. The non-dimensional displacement time plot of the system is governed by the equation 11. So this is the equation number 11. Okay, that is for 0 starting velocity for the various values of zeta. If you just see the value of zeta is greater than 1 as shown in figure, this one, figure number 3. In all these curves, the system comes to the equilibrium position in nearly an exponential manner. Higher the damping, more sluggish is the response of the system. This may even be seen physically that higher the damping, more resistance to motion is there, and therefore slower is the moment. Theoretically, however, the system will take infinite time to come back to the equilibrium position once it is disturbed from it. This type of motion is called aperiodic motion. Now, if you look towards the every value of zeta with us, here in this case the value of zeta with us 1, 2, 5, 10 and infinite. Every line drawn here, okay, so every line vibrating, okay, towards the one side of this one time axis, means this is the case of aperiodic motion. It will take infinite time to reach towards this axis. Okay, next one, analysis of critically damped system. When value of zeta equals to 1, so in this case based on again equation number 8, so equation number 8 is here. So in this case when value of zeta equals to 1, so if you look towards this relation, S12 equals to minus zeta plus minus square root of zeta square minus 1. When the value of zeta becomes 1, means 1 square minus 1, this term becomes 0. Means in this case what we get, S12 equals to minus zeta. So in this way we can get the values of S real and equal. Here the negative, no doubt negative number found here, real and equal values for this s equals to s2 equals to minus omega n. The solution of the differential equation becomes, so already I have seen the different general equation, general solution for the equation. This equation can be written like this one: x equals to c1 into e raised to s1t plus c2 into e raised to s2t. But because of the roots are equal, the extra term here c will comes into picture. So x equals to c1 into e raised to s1t plus c2 into t into e raised to s2t. Okay, this is the general solution in case of critically damped system. Okay, so in this case you have to replace this s1 and s2 term by minus omega and here minus omega. Okay, minus omega n. So we can get the value for x in this way: c1 plus this one c2t as e raised to minus omega nt. This term is common, just take this term common and give equation number next for this one, equation number 12. The above equation is the solution for the system having critically damping. For finding the values of two arbitrary constant c1 and c2, we have to take the same set of initial conditions as given by equation number 10. Differentiating equation, this one 12 with respect to time t. So already we know the initial condition, this one x equals to x naught at time t equals to 0 and x single dot equals to 0 at time t equals to 0. So by applying this initial condition, okay, so first of all, before application of this initial conditions, it is very important to take the differentiation of this equation number 12 with respect to time t. So x single dot equals to, you have to differentiate this term. Okay, so first of all write this term as it is and differentiate this term. Okay, so this is the constant, derivative of constant becomes 0 here. So here the c2 will remain. Okay, c2 into e raised to this term will remain as it is minus next one this term. Now this term will remain as it is and differentiate this term. Okay, so e raised to this term will remain as it is. Again derivative of this term is nothing but the minus omega n. That's why the minus sign is given here. Okay, so substituting the initial conditions of the equation in, we know this initial conditions. So initial conditions are here. You have to just put this initial condition in x equation as well as x single dot equation. So x equation is here. You have to just replace this x by x naught like this one, and time t here just substitute the value for time t as 0 here, t as 0, e raised to 0 means 1, this term becomes 0. Okay, straightforward we can get x naught equals to x1. Now in this case just replace this x single dot by 0. Okay, as the second condition with us, this one x single dot equals to 0 at time t equals to 0. Okay, so apply that second condition on this equation. Okay, so this becomes 0 equals to c2 into e raised to this t becomes 0 means e raised to this term becomes 0, e raised to 0 means 1, so c2 only comes here minus. So what's about this one, c2 multiplied by time t is 0 means c1 plus time 2, here this term becomes 0, so omega n, this term becomes 1, e raised to 0 means 1, so only this term will remains 0 equals to c2 minus omega n into c1. Just solve these two equations, get the value for this one. C1 straightforward we can get x naught, and c2 we can get, just substitute the value for this c1 as x naught, and we can get the c2 equals to omega n into x naught. Now substituting the values of c1 and c2 in equation number 12, so we can get the x equation. So x is nothing but c1 already with us x naught. Okay, replace this c1 by x naught plus c2 with us omega n into x naught. Okay, here. So after readjusting this equation, we can get the final equation for this x in this way, x equals to x naught into bracket 1 plus omega n into t into e raised to minus omega n t. So give equation number next for this one. The value of x in the above equation can be shown to decrease as t increases and ultimately tends to 0 at t tends to infinity. Okay, the non-dimensional displacement time plot of the system is as shown by this equation. Okay, is as shown in this figure. Okay, as well as this represent the critical damping. Okay, when the value for zeta is 1. Okay, as well as this curve. Okay, as the dotted curve, this is also an aperiodic motion, and in this case the displacement time curve lies below any of the curve for the overdamped system. Okay, now the next case with us, that is nothing but the analysis of underdamped system when the value of zeta is less than 1. In this case, the roots are complex conjugates and are given by, so can get that roots by this relation s1 equals to minus zeta plus j into square root of 1 minus zeta square into omega n, and second root you can get in this way. Look towards this equation number 8 once again. When the value of zeta is less than 1 means zeta and 1 will changes their place. Okay, so because of changing the place, so what we get here, the roots becomes complex conjugate. Okay, so roots we can get like this one, s1 and s2. The solution of the differential equation becomes, solution already we know, c1 into e raised to this term s1t plus c2 into s2t. Okay, so s1 already this value with us, just replace this s1 by this term, s2 by this term. This equation can be written as, so you have to just write this equation in a such a way that we can just do the further analysis. Okay, so e raised to, just multiply by this term to inside terms. Okay, and just separate this e term like this one, e raised to minus zeta into omega nt. Okay, if we multiply by this term to inside term, easily we can just separate this e raised to this term, and e raised to this term can just write it here like this one. Okay, so c1 into e raised to j into square root of 1 minus zeta square into omega nt will come here. Similar case with the second term, c2 into e raised to minus j into square root of 1 minus zeta square into omega nt. Now using the relationships, e raised to j theta, instead of I theta just consider j theta equals to cos of theta plus j into sin theta, and here e raised to minus j theta equals to cos of theta minus j into sin theta. Okay, now from equation number 11, here is the equation number 11 with us. This equation number 11 can be written like this one. Sorry, equation number 14, not 11 actually, 14 equation number 14 can be written in this way. Write this term as it is c1 e raised to, already we have seen in this case, e raised to j theta. Okay, j theta means here the cos of theta, theta term is nothing but, okay, this term indicate the theta, so cos of theta means here square root of 1 minus zeta square into omega t. Okay, this term indicate the theta term. Okay, this one, this term indicate the j into theta, this term indicate the theta term. Okay, plus j into sine of, once again this term is nothing but the theta term. Okay, plus next one j, you have to write it this one, This is nothing but a second one, this one C2 into cos of this term. Cos of theta means once again this term you have to replace this one. This term will come here. Cos of theta means square root of 1 minus zeta square into omega t minus j into sine of theta means this term will occurs as it is, this one as it is. Or we can just multiply by this constant term to inside term. Okay, this multiply by this term, this multiply by this term, and pick up the cos term together and sine term together. So we can just get this equation like this one: x equals to e raised to minus zeta into omega nt into bracket c1 plus c2 into cos of square root of 1 minus zeta square into omega nt in the first bracket, and in the second bracket j into c1 minus c2 into sine of square root of 1 minus zeta square into omega nt. Nothing but equation number next 15. In equation number 15, constant c1 plus c2 and j into c1 minus c2 are real quantities, and hence the equation can be written as x equals to e raised to minus zeta into omega nt into bracket a into cos of square root of 1 minus zeta square into omega nt plus b into bracket sine of square root of 1 minus zeta square into sine into omega nt. Okay, bracket complete. Or x equals to a1 into e raised to minus zeta into omega nt into bracket sine of square root of 1 minus zeta square into omega nt plus phi 1. Either you can get the right for x as this value or this one. Okay, both are nothing but the correct one. The above equations represent oscillatory motion, and the frequency of the motion is represented by omega d equals to square root of 1 minus zeta square into omega n, where omega d is the damped natural frequency of the system. Constant a1, this one, constant a1 and phi 1 are determined by applying initial conditions. The typical response curve of an under damped system is as shown in figure number 6. So in this way the system will respond. System response means here amplitude versus time. Now if you look towards for the underdamped system, this one amplitude crosses the time axis. If you look towards the previous two cases, the amplitude vanish before passing towards the next side of that axis. Okay, so applying the initial conditions, these are nothing but the initial conditions: x equals to x naught at time t equals to 0, and velocity, that is x single dot, equals to 0 at time t equals to 0, and finding the constant a1 and phi 1. We get the value for this a1 and phi 1, you can get the complete solution for this one. Okay, so complete solution x can be obtained like this one: x naught equals to x naught divided by square root of 1 minus zeta square into e raised to minus zeta into omega nt into bracket sine of square root of 1 minus zeta square into omega nt plus tan inverse of this one square root of 1 minus zeta square divided by zeta. Equation number next. This term, first term, represents the amplitude of vibration which is observed to decay exponentially with time. Now if you look towards this one, amplitude versus time plot with the zero initial velocity for all the cases. Now look towards this one, this case. This is the case related with the critically damped system. Okay, this system here, this one, this response touch with the time axis. Okay, so this is also a periodic motion. Now here in this case, when the value of zeta is greater than 1, overdamped system. Okay, here in this case the amplitude not crosses towards the another side of this axis. Okay, this is the case of overdamped system. So this is the case of underdamped system when the value for zeta is less than 1. Okay, if you just say this will reaches up to time axis within the certain period. Now this is the case when no any resistance occurs for its motion. Okay, this is the case of undamped system. I hope in the today's lecture the concepts regarding overdamped system, underdamped system and critical damped system cleared you. Thank you.